Assalamu alaikum. Myself Sumaya Israt Moin, lecturer, Department of Mechatronics Engineering, Russia University of Engineering and Technology. Today we are in the first day of International Conference on Automation Control and Mechatronics for Industry 4.0. Current time is 7:10 p.m. Bangladesh Standard Time. I would like to welcome all of you in the keynote session 4 of ACMI 2021. On this special occasion, we feel honored to have Professor Dr. Latifur Khan from the University of Texas at Dallas, USA as a keynote speaker. ACMI 2021 has got a new dimension to have a resourceful person like him. So dear audience, this is the time to welcome our honorable keynote speaker, Dr. Latifur Khan, with big round of applause. Thank you for your appreciation. It's our immense pleasure to have.
May I brief about Latifur Rahman Khan? It will be very good for me. Maybe I.
Yes, sir. The floor is yours.
Okay. So I may brief about our honorable speaker. So Dr. Khan is an international leader in big data analytics, a key aspect of data science, and he has been instrumental in educating the students in BDA at UTD for several years. And he was also successful in writing multiple proposals to NSF and getting funding for experimental research, and introduced his BDA students to research projects. His BDA class has often had enrollments of around 130 and is extremely popular. He has also developed a BDA framework and collaborates with faculty at EPPS and share his framework with them for their application in political science. Together with EPPS professors, as well as through other collaboration, he has brought in millions of dollars in federal funding in this area. And he is known worldwide as the data science person at UTD by the eminent researcher, and I think he will continue to play this role. Dr. Khan is currently a full professor in the computer science department at the University of Texas at Dallas, where he has been teaching and conducting research since September 2000. He received his PhD and MS degrees in computer science from University of Southern California in August of 2000 and December of 1996 respectively. And Dr. Khan is an ACM distinguished scientist and a senior member of IEEE. He has chaired several conferences like IEEE Big Data 2019 and 20th Pacific Asia Conference of Knowledge Discovery and Data Mining. And he serves as associate editor on multiple editorial boards. And he has conducted several tutorial sessions in several prominent conferences. And prior to coming to the USA in 1995 for his graduate education, Dr. Khan obtained his BSc degree in computer science and engineering from Bangladesh University of Engineering and Technology, Dhaka, Bangladesh, in November of 1993 with first class honors. And he was a recipient of Chancellor Awards from the President of Bangladesh. And Dr. Khan is the co-founder of Knowledge and Security Analytics, a spin-off company from the University of Texas at Dallas, developing products in data mining for social networks and data mining for malware detection. And this session is basically, the title is Data to Knowledge, Modernizing Political Event Data, Social Media Data, and COVID-19 Image using Machine Learning. So in this talk, Professor Khan have developed the software and big data infrastructure to provide machine-coded event data from news reports, from historical and real-time inputs from the web. And the project is ongoing and will produce coded news reports based on neural language processing application across English and Spanish news reports. Human annotation and validation are conducted for data validation and cross-lingual support. Geolocation of the events is also improved for better spatial resolution. One of the main computational challenges he addressed in this work is related to the efficiency and scalability of parsing online news articles in real time. In particular, they designed a distributed system with a Apache Spark and Kafka to process large amount of news articles for event coders and the actor recommender system. And this system processes articles in near real time while generating events which are provided to end user using their REST API at UTT. They are developing tools to scrape data from social media like Twitter to extract actionable information to support fast responders for road traffic injury, which is RTI, victims in low and middle income countries. In the long term, this tool will provide new low-cost technology based on semi-supervised learning that provides simple, accurate, and reliable methods to improve the time uh, timelines, timelines and accuracy of RTI reporting, shorten response times, and enhance triage decisions by fast responders. So I think Professor Khan will demonstrate how these novel semi-supervised learning techniques can be applied to COVID-19 image classification. So I think Khan, you can start, please.
Yeah, thank you, Dr. Hawk, Dr. Fakul. Uh, so today I'm going to talk about my research, but this research more applied research. I do a lot of fundamental work in data mining or machine learning area. So if time permits, I will cover those fundamental work a little bit at the end. But at the beginning, I will talk about some of our data science work, which is more applied. And if you have any question, please feel free to interrupt me at any time. And this is a joint work between computer science and political science department. And this work in the past and currently is funded by National Science Foundation, Air Force, NSA, National Security Agency, and IBM TJ Watson Research Award. So the collaboration started 5-6 years back. At that time, a lot of political scientists are working with us. So this is the guy who works in NLP area, and I work in a data science and more data mining area. And these are the collaborators in that project. They're working at the beginning. Now we mostly focus on UTD and University of Arizona, and these are the two institutions are currently involved. Okay, so let me introduce you the problem. So just think about, we have news articles, and the news articles focus on the political news articles. So basically the domain we are focusing on the political news. And these articles will be a text data. So it will be stated in English, in our case, Arabic and Spanish, those reports. So this will be the input for our system. And what we want to do, we want to extract the event coding, machine coded event data we want to extract. So for that, we want to develop a tool. So in the past political science domain, what they do, they take those articles from stated in English and Spanish or Arabic, and then some annotator read those articles and come up with annotation like what is the source, target, and actions. So in political reports, there is a political crisis going on, fight is going on, or conflict is going on between two countries. So they will identify the source, target, and actions. So our goal is to develop this event coding in an automated way. So for that, we're going to use some NLP technique and machine learning technique that I'm going to talk about. And how this will be useful? This will be useful for political scientists later to detect, understand, and interstate conflict around the globe. Okay, so motivation behind our work is we need high quality, timely, structured event data. And so this, we call it structured data, because from the unstructured, text is unstructured data. Unstructured means is a bag of words. So from there, we want to extract some of the structured data like source, target, actions between two entities. And once we identify this structured data, that can be useful for visualization purpose and further analysis and so on. So our goal is to identify those machine coded event data, what we call it structured data, from this unstructured text. And machine coded event data, in our case, we can define the source of the event when an event happens. So an article we are considering, the article can be stated in an English, Spanish, or Arabic text. And from there, we want to identify the source of the event. The article will represent or capture some event. Our goal is to identify the source of the event and the target of the event and what political action is going on and where the incident took place or event took place. So these are the things we want to extract, and that we call it machine coded event data or structured data. And our case, just think about that. Our goal is to identify the actions, and the actions can be stated in 4 types of political actions. 2 are associated with the conflict, verbal conflict and material conflict, and verbal cooperation and material cooperation. And there is a one more class or the categories, what we call it, make a statement. So when we parse those texts, our goal is to identify what type of action is going on, whether it's a political conflict or material conflict or verbal conflict or verbal conflict or material conflict, or the verbal cooperation or material cooperation, or it can be a statement. This type of things we want to identify. So you can think about, we have an ontology or taxonomy or knowledge base. The root will be some dummy node, and then a root will have 5 children. One of them is a make a statement, the other 4 will be something like this. And then they can be further categorized into finer grain like this. Under verbal conflict, we have investigate and so on. So that way, I think we end up with a total 20 categories. So at the 3rd level, we will have 20 categories like this. So now just think about, I gave you a text document, and one of the sentence in the text document is like this. And this is a little bit old text document that talks about former British Prime Minister Theresa May is doing something in the European Union. So from this text or sentences, our goal is to identify the structure, political event coding or structured data, what we call it, what is the source and target, and what is the action going on. So who did what to whom format. So in this case, since the human has a lot of knowledge, so from the knowledge, we know that Theresa May is a part of the Great Britain government. So the source will be a Great Britain government. And then the target will be European Union. And this is some sort of action is the formal agreement. And this is the code. So this, we call it machine coded event coding. And that type of thing, we want to do it in an automated way. So input for our system will be a bunch of raw text. And from there, our goal is to identify the source, target, and action. So now how we can do it? There are a lot of ways you can do it. At the beginning, I will show you very naive approach. Then later I will talk about some of the advanced NLP technique, natural language processing. So in the past, political scientists used to solve this problem this naive way. So they take in the document, they will have multiple sentences. Usually they take first 5, 6 sentences, and each sentence they will parse it and identify the verb and the noun phrases. And then there will be a dictionaries, and the dictionary will give you the verb or action. So I showed you there are 20 verb categories. So for each verb, there will be a pattern they look for. So some sort of phrases will look for. If there is a match happens, then we can say that verb is found. Identify the action or the verb pattern. So recall that we have a taxonomy or ontology. In the ontology, I showed you there are 20 concepts, right? And each concept in that dictionary or ontology, we will have some patterns. So if you see these patterns, then there is a match is found. So that way, we will, if there is no match found with the verb, then no event code will be generated. But if the match is found, then we will look for the source and target. So for that, we are going to use the political actor dictionary. So here we are talking about actors, political actors, like Theresa May is a former Prime Minister of UK, United Kingdom, right? So she will be listed here as a political actors. Like right now, the Joe Biden is the president of the United States, so he is listed here as a political actors. So the problem is this political actors is evolving. Keep in mind that in Afghanistan, there is a political conflict going on in a continuous basis. So new political actors are emerging. So in that case, this actor dictionary may not have up-to-date political actors. So this might be a potential problem. I will tell you later. But anyway, so here, based on this political actors, we will have the actor name, and then the actor association and the role, which country the actor belongs to, what is the political role, those type of things will be listed there in this actor dictionary. So once we have the source and target, we'll try to match with the political actors. If there is a match happens, then we will say that source and target are found and the event will be generated. But there is a possibility that in this case, no verb is found in the dictionary, or no political actors are found. So in that case, even event will not be generated. So as we said, there are our political actions will consist of these 4 activities: pass, make a statement. And we use verb pattern dictionary. It will be useful for identify political interactions for a given sentence. And actor dictionary will be used to identify the political actors. And this will be a big data problem. Why is a big data problem? Because we crawl a lot of political news articles every day, and this generates over time humongous amount of data, and data are coming in a real time and continuous basis. And we deal with the unstructured data. This is a text, and the text can be multilingual also. So in that case, we deal with the varieties. So that big data should have a bunch of these. High volume, velocity, varieties, veracities. So we have certain these are present here. So in the political news article, so therefore this problem, event coding problem, we can treat as a big data problem. So now let's talk about framework. So here we crawl the political news articles from the Guardian, New York Times, and then Washington News, all these sources we consider. And then from there, we crawl the political news articles. And then we use Stanford Core NLP to parse the text, basically identify the name entities and then the verbs. And then we want to scale up this processing. That's why we utilize Spark, which is a big data technology NoSQL system. It works in a distributed manner over the commodity hardware. So we utilize that here, basically do parallel processing to speed up this, to process a large number of documents in parallel. Then Once the Stanford Core NLP gives you the parts of speech and the name entities, then we will use the Cameo dictionary. Recall that Cameo dictionary contains, what does it contains? In this case, we will use two dictionaries. One is the verb dictionary, what we call it, the knowledge base, all the verb patterns, and then the political actor dictionary. So this will tell you that whether the verb is found in the sentences. If it is found, then we'll look for the source and target based on the political actor dictionary. That way, we'll generate the event coding. If there is no match found, then the event coding will not be generated. So once we identify the event coding, then we will extract the location information where the event took place. So for that, we use our own tool. If time permits, I'll talk about these tools more details. And that way we will generate the source, target, action, and the location information. And for that raw text, we will extract the metadata or event coding and put those event coding in a NoSQL system. In this case, we use MongoDB database. Okay, and so here is a one sample document. So this side represents the raw text or the document itself that we crawl it. And now from this raw text, we want to identify the machine coded event coding. So basically we want to identify or extract source, target, and action. So what is the source here? They talk about something with the Italian government business. And then the target is the DU, Germany. And what is the action? Where is the action? Yeah, action is the 01 is a make a public statement. So that type of action is a code. So the verb action is 010. So 010, we know that make a public statement. So this way, given a raw text, bunch of sentences may present, we will extract metadata or event coding like this. So that's our goal. So far I showed you high level how the political scientists used to work in this domain this way. And then the problem is what we observe in this solution. These are the problems. The solution heavily relies on the verb dictionary and the political actor dictionary. And the problem is when we parse a bunch of text document, we see many cases we cannot generate the event data. We cannot generate the event coding. Basically, no event will be generated for a given text document. The reason is either the verb is not found in from the Cameo verb dictionary. We cannot match it with any verbs here what we found in the text document, or the verb is found but the political actor is not found. So in that case, no event will be generated. So this is the problem. And for the first problem, we try to tackle it. If the dictionary is political actor dictionary is not comprehensive, as I told you. So in that case, it will be difficult to generate the event if the political actor is not present in the dictionary. So our goal is to identify or recommend new actors for the Cameo dictionary or political actor dictionary and find the roles. So how we can do it? But keep in mind that this political scientists are not computer savvy, so they don't. They just use the R for programming, and they don't make the dictionary up to date because a cost is involved. And if we want to process very large number of articles, so in that case, we will encounter this problem frequently. So our goal is to make sure the dictionary is up to date, and that will be done through you can do it in one way is ask the human to provide the new actors. When you involve human, it will slow down. It will create. It will not expedite the process. So it will create problem. Basically, slow down the whole things. And then Also, another problem is you need to hire human and pay him or her. So cost is involved. So that's why we want to do in an automated way. So how we can do it? So there are a couple of challenges. The challenge is political actors may come up with many names. Say former president of the United States, Barack Obama has a various name, Barack Hussein Obama, Barack Obama, Obama, and so on. And the political actor role may change over time. Former president of the Israel, Shimon Peres, has multiple political roles. He was a general, then he was a president of the Israel, and so on. So we have to capture all of this. And furthermore, we have to process large number of text articles. So I will show you, we develop a distributed real-time framework for that to identify the new political actors. And this algorithm is very naive algorithm, is based on the frequency. And it also recommends the roles. So what we observed, former President Trump, when he was elected in 2016, at that time, he was not listed in the actor dictionary as a political actor. He was listed there as a businessman. But he just, at that time, he was just inaugurated in 2017 in January, he came into power. So at that time, he was not in the actor dictionary. And at that time, many articles, political articles are talking about former President Trump. So now our goal is a case study. Our goal is to identify this will be a new political actors and recommend that we should add him in the dictionary. So how we can do it? So in the window 1, window 2 means, let's say this is week 1, we process large number of text documents. Window 2, we also process large number of text documents. We parse those text documents and identify the name entities. And many name entities talks about, say, Trump. But Trump is not listed there in the political actor dictionary. So therefore, we cannot generate an event. But we identify that many cases, many articles are covering Trump. Now, if we see in the window, Trump name entities are frequently mentioned, then we can recommend that Trump might be a new potential political actors. So that might be straightforward. Now, the problem is what political roles we can assign to this person, to Trump. So what we observed when Trump was mentioned in the article, he was mentioned along with, say, Hillary Clinton. He was mentioned with Obama. He was mentioned with Al Gore or Russian. What is this guy now? He's still in power. What is his name? Okay, so, Putin.
Mr. Putin.
Yeah, Putin. Yeah, very good. Putin. So these are the entities you will find, and because these are very popular political actors, so they were there in the dictionary. So that's why we can easily find their as a political actors and their roles. Now, what roles this guy will play? One neighbor, you can think he has an interaction with 3 existing political actors in the dictionary, and all are US Gov. So you can say probably he will also, based on the level propagation, you can say that probably Trump will have a role also US Gov. But also you can recommend a Russian Gov as a role and so on. So these are the possibilities. So this is the rough idea how I address that issue. So again, we crawl a bunch of political news articles, and those news articles, when we do the name entity extraction, we're using Stanford Core NLP, it gives you a bunch of entities, name entities, but we cannot find in the political actor dictionary, and it will be frequent across those window or batches. So now our goal, we may recommend that this might be a new potential political actors. Then we have to find the roles, and this person, the name entities we are extracting that are associated with some of the existing political actors, and those existing political actors may have some affiliation or roles. that will be propagated to this new possible political actors role. So that's the rough idea. And as I told you, the problem is political actors may have various names. So in that case, in that raw text, you cannot say that the people will always say Trump, Trump, Trump. Some may say Donald Trump, some may say something else, or stupid Trump, something like this. So in that case, you may need to do the cluster them together, or make sure that this all represents the same political actors. So for that, we use some string matching based on the mean hash or edit distance, and then threshold based approach will be used to group them together. And then in the window, if certain articles are frequent with the top n actors, then we will say this might be a potential new actor. So these are the ways we did it. And we tested our algorithm for a number of political actors. So intentionally, we removed those are the political actors from our dictionary and try to identify whether our system can pick up those political actors. Basically, our system can find those political actors with a high confidence, and then it suggests some roles also. Many cases it works, some cases it may not work. So for example, this is a Filipino president, is still in power, and these are the roles our system suggested. Okay, now I want to talk about the new topics. What we call it. So this is our old work. So I will talk about some of our new work. Let me talk about that new work first. Okay, so this is a very brand new work. So here we use BERT. BERT was developed by Google researcher very recently, I think 2017, and is very popular in the NLP domain. So we're trying to use BERT to handle our problem. So what we do, as I told you, that our goal is to identify the who did what to whom format, and the input will be unstructured text that we already talked about it. And from there, we want to do the structured coding or event code we want to generate, that we call it source, action, and the target. That I cover it, but we want to solve that problem using BERT. And at the same time, we want to extract the span of the text. So instead of saying British government, we want to say this part of the words will belong to who, and this part of the words will belong to the belong to whom, and this part of the words will belong to, or phrases will belong to the location. So that type of thing we want to do. Here is an example. So let's say this is one sentence, and that sentence, if I use who did what whom format, here the who is US and to whom is Israel. So basically source is US, target is Israel, and then the action is wants to help. And action is, I think, cannot see. Okay, so whatever the action I put, an action code. So that we call it source, target, and action we want to extract. And we can also extract in this form. And then for the second sentence, we want to who will be this and whom will be this and the what will be this. And this will be in, if I want to do the machine coded event coding, so these are the things I want to extract. So for that, we are going to use, okay, so we are going to use BERT, bidirectional encoder. Basically is based on the deep learning and some advanced NLP technique, LSTM model will be used. So here, if you use the BERT for the encoding, and then on top downstream task, you use some classification model. So in that case, you can do who did what to where format, we can extract it. And then we can also extract the action, what type of action, verbal cooperation, material conflict, and so on. But if you want to extract the span of text, then this may not be a good choice. The classification, treat the problem as a classification problem. So the better solution is, in that case, maybe the sequence leveling. You will give an inputs, number of input sequence, and it will produce an output sequence. So if you use the sequence labeling on top of the BERT as a downstream task, so in that case, you can extract the span of text, and then you can also capture the arguments for the training domain and so on. So here is an example what I meant. So now the input will be given to this BERT based on the pre-trained model. So this is the sentence. Obama said he would not provide support to Israel at the time he mentioned. And then there is a two downstream task. One is the classification task, and the other one is the sequence level. And here we are using multitask learning because we have a two tasks here. That's why it's a multitask. And the classification task or head will do the action, identify the verb action. So this will be treated as a classification problem. So it will try to identify whether there is a material conflict, verbal conflict, material cooperation, verbal cooperation, those type of things. For this sentence, it will label it as a verbal conflict. So maybe 5 classes will have. And then this case, it will identify, using the sequence labeling, it will identify the source and target, and source span of the text, it will emit for the sequence labeling. For the who, it will identify the Obama, to whom it will identify the Israel, this span of text. Now, so this way the sequence labeling will produce the output. Now, our ultimate goal is to produce, instead of Obama and Israel, we want to produce event coding. So Obama is related to US Gov in the past. So US Gov should be emitted, and Israel for we want to generate the code Israel. So that can be done with this ACMI dictionaries. So these two things we will combine. So we develop a framework called multitask learning based on the BERT for coding the political event data. So that based on the BERT, on top of it, we develop or come up with a downstream task where we do the classification and the sequence leveling, plus we use external dictionary to generate the event coding. And we tested our result on this on the political news article domains. So we have, these are all baselines. PETRAC is the political science baselines, so that I showed you at the beginning, our naive approach. And then UDPIPE, which handles the multilingual data set, and LSTM, which takes into consideration the dependency, the sequence dependency, and then the multitask learning based on the BERT. And based and large, the difference is the network, how many layers you will use. And here we report the result based on the source target. And F1 score, you can see micro and macro, both cases, our model is outperforming baselines. And then here we showed you source target action and the overall result with respect to the baseline. So you can see here our model is outperforming the baselines. So that clearly shows that the first approach we developed, that is outdated. So we need to use some advanced model like BERT. And now I want to show you our most recent work that we are working on. We are proposing a new, we are trying to extend the BERT called conflict BERT, a pre-trained language model for political conflict and violence. So the problem is with the BERT is pre-trained transformer model using very large scale unlabeled text. But this large scale unlabeled text, they consider the very generic text, is not focusing on the political news articles. So our goal is to build a BERT model based on the political news article itself. So that way it will be trained better and it will learn the way better way. It can perform, it can handle the political news queries or questions or classification tasks more effectively. Okay, so our goal is to develop a pre-trained transformer conflict BERT on domain corpora to help accelerate research in conflicts of political science. There are 3 tasks to be solved: data preparation, model pre-training, model evaluation. Okay, so there are a couple of ways you can build a BERT-based model. One is you will take like what Google does. Google takes 23 gigabytes of text and build a BERT model, all this transformer-based model and so on. So that we can use it. That way we will train our model on the generic corpora and come up with the weight, and that weight will be used for the downstream task. So that we call it pre-trained model. That's the traditional approach. And then another approach is, instead of using the generic corpora, why don't you consider the political news articles corpora or the domain corpora or conflict corpus, and then from there you will build the model from the scratch. So that's we are trying to do it. Another approach is you may have some generic corpus, and then you will have the domain corpus, and from these two you will learn the weight. So that we call it continuous training. So you may train it with the generic corpus, then you will update based on your domain corpus continuous basis. Or another extreme is domain corpus you will consider. From there you will build the model from the scratch. So these are the 2 things we are considering. And once you have the pre-trained model, then you will do the fine-tuning for validation. In our case, we will do the validation data set where we will fine-tune, and then we will do the downstream task. And these are the models, already some of the existing models. So for example, BERT is a general model. They train it on the wiki plus books and 3.3 billion words, 16 gigabytes of data is used by Google. On the other hand, if you consider the public MED BERT, which is a biomedicine domain, and it is built from the scratch, it considers 21 gigabyte of data, focusing on only the biomedicine data. So similarly, for healthcare domain, this is another data set, another model they built. So in political science, we don't have that type of domain targeted model. So we are the first who is developing this. So we consider the organization news government reports. From there, we consider 34 gigabyte of data and build the conflict BERT. And these are the raw data set we use to build the model from the scratch: expert domain corpus, mainstream media collection, gigaword data, Phoenix real-time PRT data, Wikipedia data. From the Wikipedia, we only focus on the political news or conflict-related articles. So these are the distribution, what percentage goes to where. And then these are more details about the data set. Okay, so then once we build up this model, we propose a comprehensive benchmark in political and conflicts domains. Conflict BERT is developed, and then we tested on the 15 data set for 20 tasks. Some of the tasks is simple classification task, and binary classification, multi-class classification beyond 2 class, or multi-level means each document may have more than 1 level, and event status classification, sequence labeling, location extraction, name entity recognition. So these are the tasks we focus on, and the results will be reported based on this matrix. And here I showed you some of the results. So conflict BERT source means So that we build it from the scratch. Conflict BERT continuous means we use the traditional BERT plus we continuously update. And this is the traditional BERT. And what is uncase and case? Uncase means the raw text may have the case, maybe case sensitive. The text, some of the words may have an uppercase, some of them may be lowercase. So if you consider that and build a model, that's one possibility. And if you don't care about it, you convert all of them is lowercase. And for BBC News 20 News, the group gun violence, we see the BERT, conflict BERT is doing slightly better than the BERT. And when you talk about police events, like there are a lot of crime happens, police did sometimes crime, some violence activities against the citizen. So that reported in this articles. So in that article, this more conflict or violent is reported. So here we treat the problem as a classification problem at the sentence level, at the document level. And you can see here, conflict BERT is doing with a significant margin. So 3 or 4% higher than the traditional BERT. So that shows that domain dependent corpus is important to train the model. So similarly, the same pattern we observe other cases. So that actually shows is a promising result. So we are planning to submit this in some conferences. And this is some of our paper. Okay, and then, okay, so now, do you have any question from this end? If not, then I will move to the semi-supervised learning. Do you have any question? Are you hearing me? Hello?
Yes, sir.
Yeah.
We are hearing you.
Yeah, so.
I think you can continue.
Okay, thank you.
I have one question. If
Okay,
we
sir.
get some time.
Yes.
Sure.
Question is that you mentioned dictionary, that is the political actors, and CAMED dictionary. So if if the situation frequently changes, say political actors changes, their political activities changes. So did you need to change your dictionary? I mean, events or actors manually, or did you have any process that?
Yeah. So yeah, in the past, these political actors, they just created, let's say they have 100,000 entries all over the political actors, for example, they maintain in the dictionary. So each actor's name, they will keep multiple variants of the names, and then they will keep the role and the time information and so on. Now, the problem is, as you said, and I mentioned that political actors are emerging over time. So, for example, even in Bangladesh, let's say 10 years down the road, new political actors may emerge, and we may not have in the Sheikh Hasina is listed there as a political actor, but if the new political actors are emerging, they may not be there. So in that case, we need to update. And the idea here is we are focusing on the printed media, right, or the news, reputed news sources. So from there, if the new political actors are emerging, so they will frequently appear in the articles as name entities. So if you see certain name entities are frequently appearing, but they are not appearing, but they are not listed in our political actor dictionary. So in that case, this will be, our system will pick it up and recommend that this might be a potential new actors. And then based on the association with the other existing political actors, will recommend some roles. And then final call, human will make the decision that this is the right political actors or not. Then once we determine that, we will add it into the dictionary.
So you need to do manually. Human assessment.
It's not fully manually. It's a semi-manual or semi-automatic.
Another question I have, just a minute. Something you did not show us, perplexity. So I am asking, what are the vicinities or what are the areas where we can be perplexed? Could you please tell us something about it? Because I think you skipped those slides. Perplexity. How could we be perplexed, or how could be
Okay, so
perplexed?
here the perplexity, I think, so when we here we do the language models to predict a mass token in unseen test case, a low. So here we define the perplexity of our model. So low perplexity will be better. So when you do the BERT and the source and the conflict BERT, these are our model. We showed that we have a low perplexity value. So that means our model, and we test on the p-test, statistical test. So that shows that our model is doing reasonably better than the BERT model based on this perplexity definition.
No, I am asking about the vicinities, where actually perplexity happen, from the user sides or developer side.
Okay, so here, here we are not doing with the user side or the developer side. Here we're talking about the language, how the language will model it. So you can think about the performance of our model. We are modeling it using the perplexity, but it may happen due to the various reasons. I think it may happen the wrong annotation, or it may happen incomplete data set. So these are the problems we have.
Okay. I got it. I got the vicinities.
Okay, thank you. Now I want to talk about our little bit theoretical work. So, I mean, machine learning work. Okay, let me. How many minutes I have? 10. Hello.
Sir,
Actually, officially we have time up to 8:10, but if you need, we can extend few minutes.
Okay, that sounds good. Thank you.
Okay.
Okay, where is the slide? Stop sharing. Okay. Now sharing again. Big data. I'm just trying to. Okay, what is slide? Screen, share screen. Okay. Okay, so you can see the screen, right? Okay. So this is the
Okay, Professor, we can extend up to 8:25 maximum.
Sure,
I
that's
mean,
fine.
we should conclude at 8:25.
Sure, I'll finish it in
Okay.
20 minutes. There will be a question answer, right? So okay, so I
A
will.
few, no problem.
Sure.
Since you are allowing the question during session,
Sure.
so maybe it will be very
Yeah.
less question answer. Okay, please.
Yeah, thank you. Pen laser pointer. Okay, so here we talk about how the machine learning can be used in real life problem. So there are two. If you from the title you should see that there's a semi-supervised learning we're talking about. You know that machine learning has there are two ways you can usually the machine learning can work. One is the supervised learning, where you need a ground truth to build the model. But usually the ground truth is very expensive and the labor intensive. Other approach is unsupervised, where you don't use any label data or ground truth. Here, so there is a compromise between these two extremes. Supervised needs a label data or ground truth. unsupervised doesn't need any label data. So we want to do something in real life. We may have a lot of unlabeled data plus few labeled data. So what we call it semi-supervised learning. And semi-supervised learning will be used to handle the COVID-related problem and the drug discovery that I will. So what is semi-supervised learning? An efficient and effective approach for training models on large-scale data set without requiring many labels. So we may have only few labeled data plus a lot of unlabeled data. From there, we build a semi-supervised learning. And why is it an important topic nowadays? Because deep learning, what is the problem with the deep learning? The problem with the deep learning, it requires a lot of ground truth to build a very effective model. It's basically resource hungry. And the cost of annotation of a data set is particularly expensive. Annotating a data set requires domain expert, and like, for example, in healthcare domain, doctors in medical domain, and so on. So semi-supervised learning is a powerful solution which mitigates the use of large amount of labeled data and optimizes the model with limited labeled data and large amount of unlabeled samples. So the key point is semi-supervised learning case, you will have very limited labeled data plus large amount of unlabeled data. So from these two, you will utilize these two set of data, you will build a model. In a traditional supervised, you will have in the training process, you will have only the labeled data. But in a semi-supervised case, you have a lot of labeled, few labeled data or limited labeled data and large amount of unlabeled data in the training time. From there, you will build your model. So this model is very effective in terms of the cost and the time. Okay, so how this model works? So there are two components. Okay, so here is an application I tried to show. So this is a chemical bond structure, and some of the labeled data we have, some of them unlabeled. And from here, if I build a semi-supervised learning, our goal is to predict that this chemical structure actually represents the cardiovascular drug categories. So how we do it? There are two things we will use in our semi-supervised learning. Our semi-supervised learning, we call it multi-contrastive semi-supervised learning framework. There are two important components in our model. One is called consistency regularization, and the other one is called multi-contrastive learning. So multi-contrastive learning is a distance learning. Basically, you will learn a distance where the similar points will be grouped together. Same class points will be grouped together, and different class points will be far away. And consistency regularization, where we use some of the labeled data and so on. So multi-contrastive is more unsupervised, and this part is semi-supervised consistency regularization. So let me tell you a little bit about these two components. Okay, so here is the idea. Let's say, I said for our framework or semi-supervised learning, what are the things we have? You have a labeled data and unlabeled data. So in this case, labeled data, if you consider the chemical structure, it will be labeled drug, or in the case of image, it will be image data. And so if it is image data, then we may have a label for the images, and then we have a lot of unlabeled data. So we do a augmentation, strong and weak augmentation, and there is a difference between basically augmentation means you will generate some more examples. In a naive way, you can think about for the images, you will create more artificial examples. So that can be done flipping, resizing, cropping, or strong augmentation can be done, color inversion, translation, these are the things. And then I said in our multi-contrastive learning, there are two components. One is the consistency regularization. The other one is the multi-contrastive learning. So multi-contrastive learning actually utilizes all unlabeled data. And then consistency regularization, we consider some sort of semi-supervised data. So here And then we combine these two learning together and do the prediction. And in this case, if it is a chemical bond structure, we'll predict one of these 12 classes. So what I meant, just think about this raw example. Let's say we have total 100 training images, and among these training images, 10 have a labeled data and 90 are unlabeled data. But these are all part of the training data. And then here we are doing, from this 90 unlabeled data, we are doing weak augmentation and strong augmentation by doing, say, creating additional examples by doing inversion, rotation, translation. That way we will generate the additional images, right? And then for the label data, we will generate some of the weak augmentation and generate some of the additional images. So that will be 10 images here. And then now we have two components in our learning models. One is contrastive loss, other one is the consistency regularization. For contrastive loss, we will use this B1 and B2 and calculate the entropy or the loss. And for the consistency I'm sorry, I made a mistake. So for consistency regularization, we will use, there are two components. One is LU and LS. I will define those. For LS, we will use supervised parts, so super label data and the weak augmentation. From there, weak augmentation images will do the prediction, and this comes from the label data. So we have the ground truth. So from there, easily we can calculate the error, LS. And then for LU is, we have 90 weak augmentation, 90 strong augmentation. And we assume that weak augmentation will be the ground for the, so just keep in mind that for a given image, we generate one, let's say, one weak augmentation and one strong augmentation. So in that case, this weak augmentation and strong augmentation are connected, right? Because they're generated from the same image. So in that case, once weak augmentation label will serve as a ground truth for an unsupervised case, and then using that ground truth, we will do the prediction. That is the LU. And then we combine these two and learn the model using gradient descent. Okay, I think I don't have that much time. So, but here, what the supervised loss is like this. This is the cross entropy, and this is the strong, I'm sorry, XS is the source, and we do the label data. We do the source label data. We do the weak augmentation, and after weak augmentation, got an image, and that image will do the prediction, and the predicted label will be Y, and the ground truth will be, in this case, because it comes from the source S, this weak augmentation, so that YS. So that way we calculate the cross entropy and calculate the LS. And then consistency regularization, it will be, the idea here is, from a given image, we construct the weak augmentation image and the strong augmentation image. So for the weak augmentation unlabeled input, we do the prediction using our model, and that model will come up with a label, let's say, and that label will serve as a ground truth. And then using that ground truth, because it's unlabeled data, right? And so, but we are doing some sort of weak augmentation and strong augmentation come from the same unlabeled data. So for there, we take the strong augmentation and predict the class label. And now the question is, what will be the ground truth? And we know that this U image, their corresponding two images we generated. One is strong, one is the weak. So weak augmentations label will be used as a ground truth for that. And then we do that way we generate the pseudo label and do the prediction. So that way we'll calculate the cross entropy, and then it will combine with the LS, and consistency regularization loss will be calculated like this. And then for the contrastive learning, as I told you, that instance wise, in the embedded space, if the points are the image come from the same class, they will be grouped together, or if they're coming from the different classes, they will be far away. So in our case, we don't have a label, but if the instances come from the same images, then they will be close together. Instances come from the different original images, then we can push them apart. So that's the main idea of the contrastive learning. And for that, we incorporate this, but and we tested this algorithm on a number of data set. So these are the image data set where we talks about airplane, cat, dog, and these are the disease data set. And when you use our multicon, our approach, in embedded space, you can see that the classes are well separated from one another. But when you use the supervised learning and embedded feature space, they're basically they're not well separated. And this diagram shows you when you run the multicon with a fewer label points, the result is very promising. With 1,000 points, it gets a very good result. And more label data points you will have, the accuracy goes up. But the main advantage of this semi-supervised learning, with the fewer label points, you can get a very quality results. So here is a more details for the CIFAR 10 image data set. So when you use 250 label data points along with the unlabeled points, you got 80% accuracy, which is better than all the baselines. When you have more data points, label data points, the accuracy will go up. And then similar observation for the other data set. Now we tested on the therapeutic classification of the drugs. So basically, these are the images, and each chemical bond structure this image represents. And each of this image will be associated with a drug, with the drug classes. So these are the classes we have. So our goal is to we generate 2 data set and do the experiment. And here you can see multicon, our approach is doing better. Even 500 label points, it is getting very good quality results. And when you have more data points, it performs better than other baselines. And this is a confusion matrix. Diagonal entries shows that how effective is our method. Okay, now I want to tell you that this algorithm can work in other domain like COVID-19, breast cancer cases, and so on. So we focus on the chest X-ray and CT scans and mammogram data set to do this, apply the semi-supervised learning. So for COVID-19, we have, these are the, just think about, we have a CT scan images. So 219 COVID images have 219 images represents the COVID-19 patient, and these are the more than 1,000 image represents the normal patients images or chest X-ray, and then the 1,000 or 1,300 shows the viral pneumonia. So here is some of the images, and our goal is to identify those COVID-19 images. And when you use multicon, with the 50% or the 50 label data, you can see the accuracy is 92%. More label data you have, the accuracy goes up, but it's still outperforming other baselines and so on. So that shows the effectiveness of our work.
Dr. Khan, could you please conclude by 2 minutes?
Sure.
Okay.
Yeah. Okay, and then, okay, so this is the things we did. And then we also did some work for the breast cancer case where the malignant, benign, and normal, and we showed that how the semi-supervised learning can work very well with a very high accuracy. So that's the end of my talk. And so if you have any question, please feel free to ask me now or email me. My email address lkhan@utdallas.edu.
Okay, thank you. Thank you very much, Professor Latifur Khan. Sumaya.
Sir.
Yes, please take your time to conclude the session.
Thank you very much, sir, for your excellent talk and the informative session. At this stage, our session chair, Professor Dr. Mohammad Fakhrul Islam, will share a certificate as a token of appreciation to our keynote speaker, Dr. Latifur Khan, and I would like to request our keynote speaker to receive it digitally.
Yeah, and thank you for the certificate.
Oh, Sumaya, you already share, huh? I am trying to share. So, Dr. Khan, please accept our appreciation.
Sure, thank you very much. And I again
you are
appreciate.
welcome.
Ladies and gentlemen, it is time to appreciate our honorable session chair and co-chair. I, on behalf of the organizing committee, feel honored to share the session chair and co-chair certificates. Now I will open the certificates for session chair and would digitally like to request our session chair to receive it.
Okay, thank you very much.
Thank you,
Thank
honorable
you, the organizing committee. And Sumaya, please take a group photo. I think it is your necessary.
Yes, sir.
So,
Sir, we
please.
have our session co-chair, sir.
Oh, okay,
And,
please.
Dr. Rifat, sir.
Dr. Rifat
Hazari, sir.
Thank you, Sumaya. I appreciate it. And also, it was a great experience for me to learn from Professor Latifur Khan. Thank you, sir, for your time to provide keynote speech at ACMI 2021 conference. Thank you, sir.
No problem. I appreciate your time and giving me the opportunity.
Thank you, sir. It's time to capture a beautiful memory as a source of inspiration for next edition of the conference. I would like to request all of you to open your camera to complete this photo session. Thank you all for your participation in this session and make this session live. With the permission of the session chair and co-chair, I like to close this session.
Thank you.
Yeah, please go ahead. Yeah.
Thank you again. Assalamu alaikum.